Okay, so just a very quick recap of yesterday so that we are all on the same page. So yesterday we looked at some of these elements of meteorology, especially the pressure, winds, and temperature. And we learned that the pressure charts are very important for a meteorologist because it gives valuable information about these the low pressure, high pressure zones. I would look for the surface level pressure chart and the 500 millibar pressure chart if it is available. Otherwise, I will just surface level pressure chart is always available. So it's because it's from observation from different weather stations which are deployed on the ground. So in the absence of 500 millibar, I can actually just use the surface level pressure chart and try to find out the weather patterns. And on top of that, when it comes to wind, when I put the wind charts on top of this, and when I look at all of them together, then wind charts, 850 millibar wind chart is very helpful because it tells me the frontal dynamics and also low pressure systems. And it also, the 700 millibar is the steering level where if the clouds form, then which direction will they move, whether they will move west to east or east to west. So that tells me 700 millibar level tells me that. And then 500 millibar level is the level where I see instability. So if the 500 millibar chart, wind chart is dipping down or the pressure chart is dipping down, then that means the cold air is going to penetrate to the lower latitudes, and that always means that there is going to be an instability. So that the intrusion of cold air from above to below, those kind of things are seen from 500 millibar level. And whenever there is an intrusion of cold air from above to below, it generally leads to formation of storms. So whenever a 500 millibar level is dipping down, then there is a chance that a good chance that there will be storms forming in that zone because of cold air hot air intrusion. And the 300 millibar level chart is basically the upper level divergence, and that is basically the winds moving out, diverging out. And that helps because when something at the top is diverging out, then that means that something from the bottom has to fill in. So upper level divergence always means a low level convergence. Can everyone mute their mics? Yeah, thank you. Yeah, so whenever you're looking for weather patterns, then the surface level pressure along with the 850 millibar, 700 millibar wind, and 500 millibar and 300 millibar wind levels help a lot. So that is what we kind of learned yesterday, and then we also looked at the different types of weather models that are being used, and what do the weather models do, and their usefulness and efficiency, and why the weather models should be taken as only a guidance, and why they fail sometimes. So that is what we looked at, and then we looked at we had a discussion about various weather patterns like thunderstorms and the convective Hadley cell, ITCZ, and all these things, which is intertropical convergence zone. Okay, so we will expand on that today, and we will talk about a very interesting phenomenon, which is waves in ocean and atmosphere, and why these waves are very important. And to me, at least personally, the understanding of these waves will give a very different perspective to weather. And I'm in the next at least 15 minutes or so, I'll try to explain why. Okay, so these waves are nothing but these are small disturbances in the ocean and atmosphere that repeat in space and time. So if you're standing at one point and if you just look at a wave traveling, you will see that it is a disturbance in the ocean and atmosphere, which will look like a sinusoidal pattern, which is shown here. Okay. It always has a number, which is a wave number is nothing but the distance between the two trough, which is from here to here. And frequency is how quickly they pass a point in a given period of time. Okay. So how many wave numbers in a specific period of time will give me the frequency. So what the waves do is they transfer energy from one place to the other. And most of the time they are zonal. So they move either from east to west or west to east. So these are mostly zonally propagating waves. But the interesting fact is that they transfer energy, although their movement is only zonal, but they transfer energy in both zonal as well as meridional direction. So they transfer energy along the movement of the wave and also the perpendicular to it. So if a wave is moving like this, then it will transfer energy in this direction, and also it will transfer energy to the latitudinal or meridional direction. Okay. And why do waves play a very important role? Because they are the connection between these modes of tropical variability which we know, which is equatorial trough is nothing but the intertropical convergence zone, which we talked about yesterday. ENSO is the El Nino cycle and Madden-Julian oscillation. All of us know all of us know these things. And yesterday, most of the discussion was kind of circulating around these three things. But the way the energy from these tropical variabilities, so these tropical variabilities, we call them modes of tropical variability because they are usually seen near the tropics. Okay, and the way they actually lead to formation of clouds. So all of these actually lead to formation of clouds. Okay, any of these ITCZ or ENSO or Madden-Julian oscillation, eventually it is seen as a cloud cluster in the atmosphere. So the connecting link between all of these is the waves. So if you take away the waves, then this cloud cluster will not form. Okay, so the waves are the connecting link between any major tropical variability and how that connects to the cloud, because unless and until the energy is transferred, clouds will not form. So the waves are the ones that actually transfer the energy from all of these big tropical variabilities that we know. The waves are the connecting point for that, and that's why they play a very, very important role. And this is today's chart. I have just taken it this morning, and you can actually how do I find waves? That would be a very good question that you may immediately post. So if I take any of these wind chart at 850 HPA, then these undulating patterns are the waves. Okay, so there is a wave pattern here, there is a wave pattern here, and mostly they will be seen near the tropics. So near the equator. So this is the equator. So phi south and phi north of the equator is where these waves patterns will be seen in the atmosphere. So this is atmospheric waves. Okay, this is not ocean wave. This is atmospheric waves. Okay, so when I start looking at these patterns, then it makes a lot of sense, because now I know that there is a lot of wave activity in the South Indian Ocean, which is understandable because your southwest monsoon and northeast monsoon are kind of in the southwest monsoon is already over. The northeast monsoon is kind of in the waning phase, which is kind of the withdrawal, close to the withdrawal phase. And ITCZ has also moved down, which is the intertropical convergence zone, is slowly moving down. And that actually indicates that the wave activity is going to pick up in the South Indian Ocean, because the southern hemisphere, the monsoon is going to get activated. If you look at this picture in March, then you will see these kind of wave activity above the equator, which is close to 5 north. And those kind of features are very important, because when these features actually coincide with the Madden-Julian oscillation kind of an event, let's say the Madden-Julian oscillation also moves into the Indian Ocean, okay, then there is a high probability of formation of a cyclone. Okay, so the waves actually play a very important role in controlling these large scale activity like cyclones. And the other reason the waves are important is because in the absence of any major tropical variability, like in the absence of let's say ITCZ varies from weak to strong. Okay, sometimes it's very strong because the winds converge very strongly from the northern and southern hemisphere. If the ENSO cycle is neutral and if the MJO is not active, then the waves can alone play a role in formation of clouds. Okay, because they are the mode of process by which energy is transferred from one place to the other. So they can solely transfer energy from one place to the other, and they can lead to a formation of a system which can dump rains. Okay, so this is the importance of waves. Okay, so that's why we try to look at these waves in both ocean and atmosphere, and how they play a role. I will in the ocean. I will talk in the next slides. because waves also play a very important role in modulating the ENSO and IOD cycles, which is the El Nino cycle and the Indian Ocean Dipole cycle. Okay, so we will talk about how they do it in the next upcoming slides.
Sir?
Yeah.
Sir, is the equatorial trough and ITCZ same, sir?
Yes, it is the same.
Okay, sir.
Okay. This is a slightly technical aspect of waves, but let me try to put it in a simple format. So there are two things when you talk about waves. There is phase velocity and there is a group velocity. So let me put it in a very simple term what this means, and because this is a very important aspect of waves, because without this meteorologists will be baffled. So what is the important point here is, so waves are, so whenever I talk about waves, go back a little bit to your physics-based knowledge here. There can be multiple, so there is something known as monochromatic wave, there is something known as polychromatic wave. So monochromatic is waves which only one wave, so only one wave which is moving, something like this. Now, I add 2 or 3 waves to it. Of course, in the ocean and atmosphere, it's not possible to have only one wave pattern because disturbances can originate from multiple places. So there can be multiple disturbances which can give multiple waves. Okay, so each of these lines are actually indicating multiple waves. So it is a polychromatic wave which has different wavelengths and different frequencies. Now, the feature of the wave is all these waves will try to interact with each other, and this is what we know as constructive interference or destructive interference. Okay, so this is something that you must have seen with waves. Either they're constructive or they're destructive. So depending on how they interact, they can be constructive or they can be destructive in the sense that their amplitude can be lower or their amplitude can be higher. When the amplitude is higher, then that means that the waves actually have a lot of energy, and when the amplitude is lower, that means the waves have less amount of energy. So this is one of the things which is represented by something known as the group velocity. And the group velocity is the single most important aspect of a wave because that is what is going to give me all the information about how the wave train is moving. Okay. So what does it do? So there is a relationship between phase velocity and group velocity. So that relationship is as follows. It is that either the phase velocity and the group velocity will be the same. That means the single wave that you are seeing. Okay, so now take this single wave. It is moving from left to right. Okay, so if the phase velocity and the group velocity is the velocity of all the waves put together, whereas phase velocity is the velocity of a single wave. Okay, so if both are same, then that means that the wave which is moving, and so group velocity actually tells you the energy, how the energy is moving in the wave. Okay, so if the phase velocity is equal to the group velocity, then that means that the wave and the energy are moving in the same direction. If the phase velocity is equal to minus of the group velocity, then that means that the wave is moving in one direction, but the energy is being transferred in the other direction, and that has very important connotation because it tells me although the wave is moving from east to west, but the energy is moving from west to east, and that actually has a very important connotation when it comes to weather because we sometimes see that the wave has passed into Arabian Sea. But then the system is forming in Bay of Bengal. So the wave is in Arabian Sea, but the system is in Bay of Bengal. That is because although the wave is moving away, but the energy is being transferred in the other direction, and that has helped in formation of a system. And that is mainly because of this, the inverse relationship between phase and the group velocity. Okay, and there is so in order to understand this, we just put two things, which is this line, which is just take a look at these two things: non-dispersive wave versus dispersive wave. Non-dispersive wave is something which is phase velocity is equal to group velocity. A dispersive wave is when the phase velocity is not equal to the group velocity. Okay, this is what you need to understand. There are dispersive wave and there are non-dispersive waves. So now we have many types of waves in the atmosphere and ocean, but the two most important ones are the Rossby wave and the Kelvin wave. Okay, so I'm sure that you must have learned about these things. If you are a weather enthusiast, you must have heard about these Kelvin waves and Rossby waves. So what a scientist or what a researcher is doing is he's trying to categorize the waves either as a dispersive wave or a non-dispersive wave. Because if I can characterize this, then I understand that this particular wave, if it is moving like this, but the energy is going to move like this, then I can actually make correlations that, okay, so although the wave has moved away, if it's a dispersive wave, there is a chance that the energy is moving in the other direction. So there is a chance that we can form a system in the Bay of Bengal, even though the wave is in the Arabian Sea. Okay, so we need to so whenever I talk about waves, I either look them I either try to see whether they're dispersive or non-dispersive. And the good thing is that there is a chart available which tells you which direction the wave is moving and whether the wave is a dispersive or a non-dispersive wave. Okay, and this is the chart which is kind of the holy grail when it comes to waves, both in ocean and atmosphere. So I'll just try to go through this. So what we have is we have a Kelvin wave, and physics or mathematical equations have told us that Kelvin wave is a non-dispersive wave. So that means that the motion of the wave and the energy of the wave is in the same direction. So that means Kelvin wave is an eastward propagating wave, which means it moves from west to east. Okay, so you look for signatures of this wave moving from west to east, and that automatically tells me that the energy is also going to move in that same direction. So that means if the wave is moving from Arabian Sea to Bay of Bengal, that means that the energy is also moving from Arabian Sea to Bay of Bengal. By energy, what I mean is the heat energy or the thermal energy. Okay, so thermal energy moving from Arabian Sea to Bay of Bengal means that the hot water of Arabian Sea is now moving to Bay of Bengal. That means Arabian Sea is going to get cooler and Bay of Bengal is going to get warmer. If it is a Kelvin wave, okay, if it is a Kelvin wave, because it is a non-dispersive wave, which means the motion and the energy transfer are in the same direction. Then you have something known as ER, which is the equatorial Rossby wave. This equatorial Rossby wave has a the Rossby waves are a very interesting aspect, because the Rossby wave moves in the other direction from west to east, sorry, from east to west, because they have a westward motion. You see, the ER is equatorial Rossby wave. It has a westward motion. The best part about equatorial Rossby wave is it is dispersive. So that means even though it is moving towards the west, but the energy transfer is going to happen in the opposite direction towards the east. Okay, so that actually puts a lot of spin to the weather prediction community, because if I see a Rossby wave and if I see that it is moving from Bay of Bengal to Arabian Sea, that doesn't mean that energy is moving the same direction, because the energy is moving in the opposite direction. And that, if you understand that, then actually you can make a lot of sense why a low pressure system is forming in the Arabian Sea or in the Bay of Bengal, and what it is going to do if the wave activity is active for, let us say, 2 weeks or 10 days or so, then what kind of things we can expect. Okay, so this wave activity is probably one of the most important features that actually makes things very interesting. Okay, then you have something known as MRG, which is a mixed Rossby gravity wave. One thing that I would like to point out about this MRG, which is a mixed Rossby gravity wave, is it has a very similar feature as an equatorial Rossby wave. It moves from east to west, and it also transfers energy in the opposite direction, because it is also a dispersive wave. So let me tell one thing here. Apart from Kelvin wave, all the other waves are dispersive. Kelvin wave is the only non-dispersive wave that you can have. All the other types of waves are dispersive. Okay, so MRG is mixed Rossby gravity wave, and this mixed Rossby gravity wave has a very unique signature where it will have a twin system. So I don't know if I have a picture of that. I don't have. So what MRG, the signature of MRG wave is that near the equator, it will allow for twin system formation. So it will form a system in the northern hemisphere, and at the same time, it will also form a system in the southern hemisphere. So whenever you see twin systems near the equator, that means it is due to a MRG wave, which is a mixed Rossby gravity wave. Okay, so that is what differentiates this equatorial Rossby wave from MRG wave, because this will have a very unique signature of two systems at the same time in the northern and southern hemisphere. And depending on which system gains energy, one of the systems will intensify, whereas other will become weaker. Okay, so that is a very unique signature of a MRG wave. And MJO, which is the Martingale oscillation, is also a wave phenomenon, and it moves from west to east. Okay, so it has a eastward motion. Interesting thing about MJO is that it is a dispersive wave. So again, my same theory applies, that even though it is moving from east to west, sorry, it's moving from west to east, MJO is moving from west to east, but the energy transfer is not happening in the same direction. So let's say the MJO moves into the Bay of Bengal, but still it can give energy to Arabian Sea. Okay, and that is what happened during Cyclone Gati, which is the recent cyclone, where it intensified at the last minute. Within 6 hours before landfall, it intensified. The reason is because although MJO had moved into Bay of Bengal, close to the southwest Bay of Bengal, but the energy was still getting passed down to that particular system. So if you understand these dispersive versus non-dispersive waves and which direction they are moving, okay, so this chart is probably the most interesting chart if you actually want to understand the wave dynamics. And note it down that except for Kelvin wave, all other waves are dispersive, and that actually means that energy transfer and the movement of the wave are not the same. Okay. So is there any doubts here, or shall we continue?
So I have one doubt. So when you are referring to energy with respect to different waves, you are referring only to thermal energy, no other form of energy, right?
Thermal and momentum. So momentum means how. So thermal is very important because that is what is transferring the hot energy from equator to other places. The other thing is the momentum, because momentum is also important because faster the wave action, faster the vorticity. So more winds means more vorticity, and more vorticity means more moisture convergence. So the speed of the wave actually tells me whether the moisture convergence is going to be high or low. So whenever I talk about waves, I look for two things. For instance, here, I'll give this example. So this wave is quite a strong wave because it has this red means high velocity. Okay. And this particular wave is actually so this is not a movie, but if you kind of do an animation of the movie, you will see that this particular wave is moving from east to west. So it is a Rossby wave. It is an equatorial Rossby wave, and it is an equatorial Rossby wave and not a MRG wave because I don't see two. So I don't know if you see this particular thing here. This is a low pressure system that has formed in the southern hemisphere. So when it is an MRG wave, then a similar kind of a thing would be seen in the northern hemisphere as well. So this is a equatorial Rossby wave because I don't see that twin systems or twin signature. So this is an equatorial Rossby wave, and although the wave is moving like this, but you can see the system has formed at the back of it because the energy is being transferred here. So so two things that I see here is the strength of the wave, and this is a very strong wave, and hence it is actually giving a lot of moisture to the system. Okay. So I look for two things. One is the strength of the wave, and the second thing is energy transfer, which direction the energy is being transferred. So thermal plus momentum, both of them.
Right. So second part of the question is, so the relationship between the wind and the waves is basically directly proportional, correct? It is basically the wind which is causing these waves.
So any perturbation, so it could be wind, it could be topography, because some of the things start from mountains. Mountains can also generate waves. So basically winds are the reason for the waves, correct, in a short form.
Okay.
But once the waves form, then they have their own feature, which is what I'm trying to explain here. So Rossby wave has its own feature, Kelvin wave has its own feature, MRG, mixed Rossby gravity wave, has its own feature, MJO has its own feature. So we need to understand all of this, and then only we actually come to a judgment that what is going to happen in that particular zone. So it's actually waves is a very complex thing. I'm just in this basic course, I don't know how to simplify it further, but yeah, the important aspect you have to understand is there are dispersive as well as non-dispersive wave, and for at least for this course, just look at these three waves, which is Kelvin, MJO, and equatorial Rossby. And if the take home message is that Kelvin wave is a non-dispersive wave, so that means the energy will move in the same direction as the wave. And Rossby wave is a dispersive wave, which means energy and the movement will not be in phase with each other. Same with MJO. MJO is also a wave, but it is moving from west to east, and it is also a non-dispersive wave. If you sorry, it is also a dispersive wave. So if you understand these three things, I think that's good enough, because that will actually give you a flavor of when you're looking at charts, and if you're looking at MJO signal, then you will actually be able to appreciate that although the MJO signal is in Bay of Bengal, but it can trigger a system in Arabian Sea. So that is the kind of thing that I'm trying to explain here.
Sir, can you please explain those charts, sir? How to see and understand this chart, sir?
So in this chart, I would say don't worry about the contour thing, these values 1.3 and all these things. Don't worry about that right now because it is too advanced. And I don't. That is something that if I start, then it is going to take a lot of time. Only thing that you should understand is the direction. So eastward versus westward. Okay, and you look at. I have actually given the three types of waves that, so I have circled the three types of waves that you should actually be interested only for this course. Let us stick to only Kelvin wave, equatorial Rossby wave, and MJO. And just understand the fact that Kelvin wave is here, so it is a eastward propagating wave, okay. Whereas equatorial Rossby wave is here, so it is a westward propagating wave. And what it means when it is lower versus higher on the frequency chart, it means that equatorial Rossby wave is a low frequency wave, which means it will sustain itself for a very long period of time. So equatorial Rossby waves and Kelvin waves, so equatorial Rossby waves and MJO, if they enter a basin, they have the capability of staying in that basin for 15 days or 20 days at a time. So that is what these, if anything, if any of these waves is within this band in frequency chart, then it means that these waves can linger around for a very long time in that ocean. Kelvin wave is a fast moving wave, so that means that it will stay in the ocean for only 7 days or so. Okay, so this is good enough for this particular course right now. Let us not make it complicated because it's easy to get lost in
sir.
this side.
And one more question, sir. I heard about that Fujiwara effect, sir. Is it due to mixed Rossby gravity?
No. Let's not. That is in cyclones. Let's not confuse that. Okay.
Okay, sir.
Okay, so the waves keep traveling, and this is again what I have shown. Same thing I'm reiterating. Equatorial Kelvin wave is moving from west to east. Rossby wave is moving from east to west. So as the Kelvin wave moves, the energy will also move in the same direction. However, when a Rossby wave is moving, there is a high probability that although the movement is like this, the energy is moving in the other direction. Okay, so that clearly means that there is a highly nonlinear signal when it comes to El Nino, because equatorial Rossby. So let us take a scenario. Let me take a scenario where there is hot water here. I'm talking about ocean right now. Okay, not atmosphere. So let us assume that there is a hot water here and there is a cold water here. This equatorial Kelvin wave which is moving will take this hot water and it will start moving it to the eastern Pacific. At the same time, this Rossby wave will start taking this cold water and it will start moving it to the western Pacific. Okay, that is how things start, in the sense that if there is if there is a Kelvin wave, then there has to be a Rossby wave, because again mass conservation has to happen, because if I take water from some place and move it, then some other water from some other place has to come and fill that gap. Okay, so what happens is, we know that this Kelvin wave is a non-dispersive wave, so that means that as it is taking the water along with it, energy will also move in the same direction, so no problems there. But with Rossby wave, the issue is that although the Rossby wave is moving like this, but the cold water it is transferring is not moving like this. It is moving opposite of that. Okay, so that is the tricky part about El Nino, because for El Nino, what should happen is cold water should come here and hot water should go here. That is when El Nino will form in Pacific. Cold water from Eastern Pacific moves to Australia and hot water from Australia moves towards South America. That is when an El Nino forms. So because of this highly non-linear relationship between different waves, it is very hard to predict whether El Nino will form or not. Given today, I cannot predict whether an El Nino will form or not, because this wave action is highly non-linear. Okay. If it was linear in the sense that if Rossby wave was also behaving like a Kelvin wave, where I know that the cold water is going to move here, then I can predict things easily. But there is an issue that Kelvin wave is easy to predict, but the dynamics of Rossby wave are very hard to predict, and that is the reason why we are unable to predict El Ninos much ahead of time. On the other hand, we look for satellite images and see how these pool of water has moved, and then only we make judgment about El Nino. So we can only predict El Nino, let us say 2 months or 3 months in advance. Okay, not like 1 year or 2 year in advance, right? Okay, so timescales of atmospheric waves. Now I'm coming back to atmosphere. Kelvin wave, like I said, is a short-lived wave. It is only for 14 or 7 to 14 days. Whereas Rossby waves live for 10 to 14 days. In Rossby wave also we have different types. We have a short frequency, we have long frequency, and long frequency Rossby waves can linger around for a month or 2 months. Okay, so this is the eastward propagating Kelvin wave which you are seeing. So what this particular diagram is showing, this is known as a Hovmöller diagram. So what this Hovmöller diagram is one of the most important diagrams for finding out waves. What it does is, on the x-axis you have longitude, which is the entire globe. Okay, so the 30 east to 30 west, so covering Atlantic all the way to Pacific. And here you have time. So starting from, let us say, Jan 1st, the entire year, so 365 days. So on that, you are putting the signals of waves. Okay, and when you see so blue means it is moving from left to right, and red means it is moving from right to left. So all these red patches mean it's a Rossby wave, and all these blue patches means it's a Kelvin wave. Okay, so at a time in which basin, so our Indian Ocean basin is somewhere around 60 east and 90 east. So this is where we are. So you can see that episodically we get Kelvin wave, Rossby waves, and this Rossby wave stays for a longer time, whereas Kelvin wave has a very short life, but Rossby wave can linger in the ocean for a very long time. Okay, so this actually gives us a very interesting perspective, because if I am able to kind of have this chart, then I can do a lot of predictions. At least 1 month, I can do a long range prediction for 1 month. So depending on wave action is how a long range prediction is done. Okay, depending on the wave action. So this Hovmöller diagram is a very important diagram, because and these Hovmöller diagrams are available from different places. I will show you in the afternoon session where to see such a chart. And this is again the same Hovmöller diagram which I am showing for a period of around 6 months. Okay, so this is the hindcast, which is already things which have happened, and this is the forecast. So this begin forecast means the forecast. This is the forecasted data. So it tells me whether black indicates MJO, whether the MJO is going to move into the basin or not. Red represents the Rossby wave, and blue represents Kelvin wave. Right now, don't worry about this purple line which is low. Let's not worry about that. We are only looking at these three features, and these three features, whenever they get together. So this is the cyclone. This is this month, right? I think this is this year. I don't know. Anyway, so you can see that there is a point in the second week of May, right? In the second week of May, when there was a strong Kelvin wave, there was a Rossby wave, and there was MJO. All these three things came together, and that is when the cyclone Amphen formed, and that was a super cyclone. So you can imagine why it became a super cyclone, because all these three things were very active. That means a lot of energy was present, and a lot of energy was being transferred, and a lot of moisture was also available, and that actually made this cyclone into a super cyclone. So this is when Amphen formed this year in May. So this is around 17th of May, and that is when Amphen was a super cyclone. So this actually tells me a lot of information. These Hovmöller diagrams tell me a lot of information. And you can see that during the monsoon season, the wave activity kind of reduces. Okay, so in the pre-monsoon season, the wave activity is very large. Like you have very strong wave activity, very strong Kelvin wave, Rossby waves, Kelvin wave, Rossby wave. But as soon as you come into the monsoon, the wave activity dies down. And there is a reason. The reason is because during monsoon, the monsoon circulation actually plays a very important role. So that is the single most important feature which governs the entire monsoon season. Okay. So after the monsoon season, which is October onwards, again the wave activity will pick up. Okay. So this is something which, if you understand, then you can actually so this is basically pre-season, monsoon season, post-season. So pre-season the wave activity is very strong. Monsoon season the wave activities are kind of not too strong because the monsoon circulation itself plays a very important role. And then the last one is post-monsoon, again when these activities will pick up. Okay. So Hovmöller diagrams give a lot of information, and like I said, models are a good guideline, but when you keep adding these information, then the forecasting ability becomes stronger and stronger.
Can I ask a question?
Yes, please go ahead.
So, with reference to the previous diagram that you showed, if you look at the wave activity, even across other longitudes during, so after say 23rd of May, it appears to, it looks diminished. But so where the monsoon circulation might not be occurring. So what explains that?
Sorry, so this is longitude. So this means that this is our Indian Ocean basin.
Right.
This is the South China Sea. This is the Pacific, and this is Atlantic.
Correct.
So the monsoon is pretty active only in this region, right? The monsoon is active only in the South Asian region, which is this region. In the Pacific, you don't have a monsoon as such.
Right.
That's why the wave activity will continue in that region.
Okay. But it appears, I mean, I don't know, it appears to be much lesser than, what it is between the 29th of Feb and the 23rd of May.
29th of
Feb and if around 120 degrees west, we look at,
So you're talking about July.
So yeah, I'm talking about this the 120-degree west line, or even if I look for further towards 0 degrees.
Yeah, of course. So the waves actually dissipate. See, once they have given out the energy, then what is the source of sustenance? So as the wave is moving, it kind of dies off, because after that, if it has given away its energy, then slowly it will decay. So the waves have a tendency to decay out.
Okay.
So
would it be correct to think that the monsoon circulation disrupts wave activity across the world while it is active?
Yes. So I mean, I think you have kind of asking the question which is which no one knows the answer yet, but a lot of people think this. Monsoon is the sole controller of many things that happen. So it is right to say that monsoon actually governs other things. Although till now we assume that El Nino governs the monsoon, but what the climate scientists are actually now seeing is that monsoon patterns actually govern El Nino formation, La Nina formation, IOD formation, or wave activities, because that is the single largest controller of its own that can modulate many things in the atmosphere and ocean. So you are right. I agree with that. I was going to tell that later after we finish the monsoon thing, but yeah, you're right.
Okay, thank you.
Yeah. So monsoon. Yes.
Sir, can you please explain about that background color, sir? Blue and orange, and in between white color is there, no, sir? Can you please explain about it, sir?
Which one? Sorry, I didn't.
That background color, sir. In that picture, somewhere it's blue, dark blue. Yes, sir.
Right. So this is Kelvin wave. So blue represents Kelvin.
Not that line, sir. That color I'm asking, sir. In between, it's like brown in color.
This is basically representing cloudiness. So this means that there's a lot of cloudiness, dry and wet phases. So during Amphan, it was a lot of wet phase. So green represents wet phase, and this represents a dry phase. So yeah.
Okay, sir. One more question, sir. Does waves continue in June, January, and February season, sir?
Yeah. See,
Okay, sir.
waves will be present every time. The only thing is the one. So like we just discussed, and it was an interesting point. When monsoon comes, then it can. So it is not. It is not true that during monsoon waves cannot exist. But the thing is that monsoon will control it. So the monsoon circulation itself is that one big thing that will control waves. Whereas during other seasons the waves will control other things, like during, so once the monsoon circulation is away, so once the monsoon is done, then the waves will actually have a very distinct feature. Okay, but during monsoon the waves don't show a very distinct feature because the monsoon circulation or the monsoon trough that we call, that actually kind of over dominates. Okay, so other than this June, July, August, other than June, July, August, September, October, other seasons the wave activity will be seen very distinctly in these Hovmöller diagrams.
So northeast monsoon during that season, waves only dominate, no, sir?
Exactly. For northeast monsoon, you don't have something known as monsoon trough, and you only
Okay,
have waves and MJO, and that is
okay,
why northeast monsoon prediction is little bit difficult because when I have one single dominant feature like monsoon trough, then I only track that and it helps me in understanding the monsoon pattern. But when you have these waves which are more erratic, which are more it's a disturbance, right? It's more erratic behavior. So that is why northeast monsoon behavior is very is not as clean as southwest monsoon.
okay, sir. Thank you, sir.
Yeah. So, any other questions or doubts, or shall we continue?
Sir, one question, sir. Actually the models are showing that MJO is entering Indian Ocean around the end of December. Would it impact the northeast monsoon, sir?
I don't. I mean, I don't know. See, so maybe so MJO. It also depends on the amplitude of MJO, how strong the MJO is.
Okay, sir.
And right now it is looking more like the MJO will be. See, so now ITCZ is also shifting down. So that ITCZ
Okay,
shifting
sir.
down means southern hemisphere. See, so MJO once it's in Indian Ocean, it actually affects both North Indian Ocean as well as South Indian Ocean. Okay, so
Okay, sir.
after December, the MJO usually tends to favor South Indian Ocean more than North Indian Ocean. So it is right now. It is not clear whether that will help produce a production of any system during the northeast monsoon.
Okay, sir.
Maybe it will give some scattered rains, but a formation of any strong system is kind of ruled out right now.
Okay, sir. We can see that ITs are present by that those clouds picture, no, sir. So
Correct.
okay, sir.
Anti season, and also this is the wave. This is the wave action for today, and you can see that the waves are also active in the South Indian Ocean, not in the
Yes,
North
sir.
Indian
It's
Ocean. So this kind of
south,
tells me
sir.
gives me a picture that even if MJO moves into the basin by end of this month, the wave activity is not very strong in North Indian Ocean, but it is active in South Indian Ocean. So there is not a very high likelihood that there will be a active northeast monsoon presence end of this month.
Okay, sir. But these waves are atmosphere waves, no, sir. Rossby waves, Kelvin waves.
Yeah, this is atmospheric, but they're also present in the ocean. But whatever I
Okay,
am
sir.
showing here is atmospheric waves. This chart is from atmosphere because it is wind at 850 HPA, so it is atmospheric waves.
Okay, sir. But MJO is present in ocean, so everything is mixed.
No, MJO is not in ocean. MJO is also atmospheric phenomenon.
Okay, sir. So these three waves are atmosphere, purely atmosphere.
No,
Rossby, Kelvin.
Kelvin and Rossby can also be seen in the ocean, but
Okay,
MJO is
sir.
purely atmospheric phenomenon. Like in the sense that MJO wave will only be in atmosphere, but it interacts with ocean, uh, but it is only seen in atmosphere.
Okay, sir. I'll note it down, sir.
Okay, so that is more about. I mean, so there is lot of things about waves that we can go on and on, but the simple point is that the wave activity. So yeah, so if it is getting little too technical, the only thing, if you can remember, is the dispersive non-dispersive aspect of waves. And the second thing is the movement, which direction they are moving, which is very clear because Rossby wave moves east to west, whereas Kelvin wave moves from west to east. And the third thing is the Hovmöller diagrams and how to look at these Hovmöller diagrams, because it's very straightforward because the legend is given. If there is a Kelvin wave, it will be shown by blue, and it also shows how it moves, in which basin it moves. So Kelvin wave, you will always see that the movement is from west to east, so you will always see it propagating this way. Whereas Rossby wave will have a propagation like this. You will see Rossby wave moving from in this direction. Okay, so that is all about waves. If you can pick up from this course, then that's enough for now. Right? Okay, so let us now move on to the jet streams, and yeah, so there was some interesting discussion about jet streams yesterday, and what I will try to there were some questions on how the jet stream modulates or how it moves, summer jet stream versus winter jet stream. So I will try to answer those things in this module. But jet streams actually help us a lot during winter weather. During winter time, the position of the jet stream helps us in understanding whether the winter conditions are going to be harsher than normal, or they're going to be above normal, like temperatures during the winter time. But nevertheless, they also play a very important role for onset of monsoon. So I'll explain how. So whenever you talk about jet streams, they're fast-moving masses of air that move along the globe, and please don't confuse it with MJO, because this is not MJO. MJO is so purely a wave which moves only along the equator. So MJO wave is only near the equator, and it is not a MJO is not a very high latitude wave. Okay, so it is only it only flows near the equator. Okay. So jet stream is a different kind of a wave. It doesn't have any coupling with ocean. Jet stream only is in the atmosphere. Okay, and it is purely driven by the convection that happens between equator and poles. So yesterday we saw that slide where we talked about the amount of heating near the equator and amount of cooling near the poles. That is what gives rise to the jet streams. And you have two important jet streams. One is the polar jet stream, which is near the poles, which controls the Arctic and North American climate. And then you have the subtropical jet stream, which actually controls the extratropical weather, which is India and South America and Africa and all those places. Okay, so you have two distinct jet streams that you can actually see. And these jet streams can attain very strong speeds, as strong as 300 kilometers per hour in the upper atmosphere. Okay. All right. So when I talked about jet stream, there is a further bifurcation, which is permanent jet stream, which are subtropical and polar jet stream, which are always present throughout the year. And there are temporary jet streams like easterly jet or Somali jet, which only make their presence felt during the monsoon period. So during the monsoon, there is this strong jet which moves from Somalia to India. That is the jet that actually brings a lot of moisture. And that is a temporary jet stream, because after the monsoon season is over, it kind of goes away. And the same thing, easterly jet is also very important. It plays a very important role during the northeast monsoon, where this easterly jet brings in moisture from South China Sea into Bay of Bengal. And that plays a very important role in governing the northeast monsoon. Okay, so the one difference between this is that this and this, the subtropical or polar jet stream versus these Somali jet or tropical jet, the main difference is that one is permanent, other is temporary. The second difference is that these are high altitude jet streams. Like these can only be seen around 5 kilometers or 8 kilometers above the ground, whereas these are low level jet streams which you can even see at 1 kilometer or 2 kilometers above the ground. Okay, and that is why these are moisture laden, whereas these are dry. That's why this plays a very important role during winter, because it is dry air, colder dry air, whereas this is moist warm air. So this has the tendency to give a lot of rain, whereas this has the tendency to bring in a lot of cold weather or snow. Okay. So this is what I have kind of put down in this particular chart. What is this? So this is the subtropical jet stream. This is the polar jet stream. And then you have your Somali jet, and you have the tropical easterly jet. Okay. So these four are the important jet streams, and these two are the temporary jet streams, and these are the permanent jet streams. So let us look at the permanent jet streams because those are important. So when I talk about permanent jet streams, then what happens is you have the warm tropical air near the equator and you have the cold polar air near the poles, and that leads to a formation of this wave which keeps moving throughout the globe. So this jet stream is nothing but a Rossby wave, and this Rossby wave is a different kind of a Rossby wave because it moves from west to east. Okay, so this jet stream is also a Rossby wave, but instead of moving from east to west, it moves from west to east. Okay, and it is also it's also a dispersive wave, so that means energy movement and the movement of this wave will not be in phase with each other. Okay, so let us not confuse those things right now. Let us just understand what happens to a polar jet stream. So what happens to a polar jet stream is there is a cold air, there is a warm air, and when this warm air begins to kind of become colder, okay, so then when the tropical warm air starts becoming colder, then it actually starts pinching the jet stream. Okay, because what happens is this warm tropical air will start penetrating into this cold tropical air, and it will slowly start undulating the jet stream. So this particular phenomenon is known as undulation of the jet stream, and depending on how this gradient between the equator and poles behave, finally this jet stream can pinch off and it can lead to a formation of a polar vortex. So this is that polar vortex. Okay, so this is that polar vortex that once it pinches off, it can move down. It can move from the Arctic towards North America, or sometimes as low as North India. Okay, giving intense winter condition or intense snowstorms. So these heavy snowstorms that are seen in Himachal or Jammu Kashmir, they are actually a result of the jet stream which has undulated, which is forming this vortex. Which vortex brings a lot of cold air to a lower latitudes, and thereby resulting in the formation of snowfall. So since this is moving east and since this is moving from west to east, so what happens is there will always be one cold wave followed by a hot wave. So so this is what is the disturbance we call. So once this particular wave has passed, once this polar vortex has passed, then after that, for let's say 1 week or 10 days, there is going to be a high pressure, which is high pressure is usually associated with clear and warm weather. Okay, so and no inclement rainfall or no inclement snowfall conditions. Okay, but later on, after this there can be another vortex which will come in and give a inclement weather. Okay, so so basically what I'm trying to tell is these are not stationary systems. These are moving, and they move from west towards the east. So that is why you have episodes of very cold weather followed by hot weather and followed by cold weather. So if you can actually track the jet stream dynamics, then you can actually understand the patterns of this winter, this very harsh winter, when harsh winter is going to occur. Okay.
Sir, 1 minute, sir.
Yeah.
Can you please tell how that jet stream forms once again, sir? That cold air pinching you told, no, sir. Can you please explain it, sir?
No, jet stream basically forms because of the heating between, so the differential in the heating between the equator and the poles, that gives rise to this fast moving stream of air, which is what we call as jet stream. So the difference between equator, so the difference between the temperature here versus the temperature in the pole is what gives rise to the jet stream, and it is always present. Jet stream is always present. So this is a disclaimer that this trough versus ridge. So this trough versus ridge, the difference is that this trough is the starting point for formation of a vortex. Unless a vortex forms, we don't call it a polar vortex. So this trough is not a polar vortex. Only once it pinches off, you actually have a polar vortex, and that polar vortex actually has the capability of giving very high precipitation, very heavy precipitation. So by precipitation, it could either be rain or snowfall. So for upper reaches of, let us say, North India, heavy precipitation is snowfall. Whereas as you come to the plains, which are like Delhi, Haryana, it becomes rain. Okay. So the difference between a vortex and the trough is that a trough, it will give only moderate snowfall or moderate rains. Once it pinches off, then it has a capability to give very heavy precipitation. So subtropical jet stream again is so this is what you were asking, right? The temperature contrast between the tropics and subtropics is what gives rise to this subtropical jet stream. So during winter, the subtropical jet stream is nearly continuous in both the hemispheres. However, during the summertime, it is intermittent in the northern hemisphere because it migrates up north. The reason it migrates up north is because your monsoon trough or monsoon circulation is moving, correct? So your monsoon circulation occupies all the way from Kerala to Delhi or North India, and that is why your subtropical jet stream during summer kind of becomes choppy, or it is not a continuous stream of air. Okay. And STJ, the subtropical jet stream, is closely connected to Indian and African monsoon. The reason I'm saying it is closely connected is because unless and until this subtropical jet stream moves up north, unless and until this subtropical jet stream, so during this is the summer, this is the position of the subtropical jet stream during the summer time. So it has moved up north, and that is why your monsoon is able to penetrate. So once the monsoon current starts withdrawing, this particular subtropical jet stream will also start moving down. Okay, so this movement of the subtropical jet stream up and down is closely related to how the monsoon currents actually propagate. Okay, and this is also connected to the fact that I don't know if some of you might have heard it, Siberian high or low. So what happens is in Siberia, which is here. So in Siberia, so it has been seen that the Siberian weather actually also plays a very important role in the movement of the monsoon currents, because what happens is during summertime, this Siberian air gets warmer, and as the Siberian air gets warmer, this air blows towards the Tibetan plateau, heating the Tibetan plateau and causing the monsoon to move faster. So the status of the Siberian air, the temperature of the Siberian air during winter and during summer plays a very important role, because if this is warmer, that means that the subtropical jet stream is going to move up. That means the monsoon is going to propagate faster. Okay, so it can make a rapid movement. Whereas when the Siberian air gets cooler, then the subtropical jet stream moves, and this also signals the kind of withdrawal of the southwest monsoon. So one of the withdrawal of the southwest monsoon feature that meteorologists look out for is when this Siberian region starts getting colder. Because when the Siberian region starts getting colder, this colder air moves because the winds are now blowing from west to east. So this cold air moves into Afghanistan and Pakistan, and that actually starts cooling the Tibetan plateau. And once the Tibetan plateau cools, your monsoon has to withdraw because there is no active monsoon circulation. Okay, so this is how the jet stream actually plays a role in modulating the monsoon. Or I don't see. So this is again an open question, whether the jet stream affects the monsoon or the monsoon affects the jet stream. So it has there is no definitive answer because the monsoon. So does it so happen that whatever happens here determines what happens in the Siberian region, or whatever happens in the Siberian region controls whatever happens in the equatorial region? So this particular teleconnection is not very clear. Okay, so right now what we are only doing is we are looking for signatures when the subtropical jet stream starts moving up, because as it starts moving up, then the monsoon current can slowly propagate upwards. Okay, so that is the kind of the large scale things that we're looking when we are looking at the onset of the monsoon. Okay. So polar jet stream, I am not going to talk much because that is mostly for North America, and that is also tied to something known as North Arctic oscillation, because the polar vortex is a phenomenon which is mostly for North America and not much for India. Okay, but the only thing that you have to understand is the movement of the polar vortex also has a very important bearing on the subtropical jet stream. So the polar jet stream and subtropical jet stream are kind of interconnected, because if a polar vortex moves down, then that means the subtropical jet stream will also move down, dipping to lower levels, giving rise to cold weather to many parts of India. Okay, so what we are looking for, we are always looking for this kind of a pattern. So when the jet stream dips, then we are looking for this dipping pattern, because that is what is the reason for violent weather. Okay, so I'll just show one chart here. Yeah, so for India, so if you see, this is the typical subtropical jet stream pattern. This is at 300 millibar level, and you can see that this particular jet stream has moved. It's much above India, right? So this is typical during summer. During winter time, which is right now, I don't have the picture right now. But if you see windy.com and go to 300 millibar level, you will see that this particular jet stream is now here. Okay, so I will show it to you. Just give me 1 second. Yeah, so let's go to the 300 millibar level. See, the jet stream is here. So it has moved south. So this is the south versus, so and as the summer approaches, this will slowly move north, and it will settle somewhere here. Okay, so this movement of the jet stream is very important for monsoon as well. So you can see that everything is connected. So during winter time, to give forecast of winter weather, I usually look at where the jet stream has actually settled. Okay, because even during winter, the jet stream, so like I said, the trough and ridge kind of pattern. So right now there is a trough coming in, and that's why temperatures along North India are very cold, and also in the central plains of central India, the temperatures are kind of normal, right? They are not above normal. That is mainly because this kind of a trough kind of a pattern is coming in. But when this trough actually becomes too significant, then you get violent weather, like very cold conditions, and those kind of things. So so during winter time, for winter weather, we are usually on the lookout for how the jet stream behaves. Okay. All right, so a couple of things before we wrap up is how a polar vortex forms. The polar vortex formation is basically when the jet stream is very strong, then it will contain the cold air in the near the poles. But when the jet stream becomes weaker, and the way it will become weaker is when this warm air starts moving north, and that is when you start cooling the equator. When you start cooling the equator, that will actually push the warm air to the north, and that will make the jet stream weak, and that will result in formation of these polar vortices. So now this is again, I can tie it down to global warming. So this global warming has resulted in stark variations in the temperature. So summers are hotter and winters are kind of colder. That is what is the variation that we are seeing, and that kind of ties well with this particular case, because during winter time, when your equator is cooling at a faster rate, that means the jet stream is going to undulate at a faster rate. So this undulation of a jet stream is going to allow this cold air to move further down south. Okay, so that movement of the cold air further down south means you can expect very harsh winter even in central parts or even in southern parts of India. Okay, which was not the case probably few decades back, but because of the undulation of the jet stream, these extremes have actually increased. Okay, these extremes have increased because the way we are heating and cooling the equator and the poles are changing. Okay, so that is one aspect that we should all understand why the extremes have increased. Yeah, so when the temperature gradient between the equator and the pole is very high, that means very warm air near equator, very cold air near pole, then this is a stable polar vortex. But when the temperature gradient starts to reduce, so when either equator starts getting colder or the pole starts getting warmer, which is exactly what is happening because the polar ice cap is melting. So when the temperature difference between these two, equator and pole, starts reducing, then you start producing these undulated structures of jet streams, and that is not good at all. Okay. So along with the jet streams is associated this western disturbance, which is what gives winter rains to northern part of India. So northern part of India doesn't get too much from monsoon. I mean, it does get a lot of rain from monsoon, but the winter rain is also very important for rabi crops, because the winter crops are the ones which are mostly in the northern part of India, or Rajasthan and Haryana and all those places. So this western disturbance induced rain is very important. So what this western disturbance actually does is high pressure during the winter season, not a persistent high pressure, a high pressure which varies. Okay, so sometimes a high pressure kind of exists over the Ukraine region, and that actually pushes the winds from the Mediterranean Sea all the way to India, coming through Afghanistan, Pakistan, and coming towards India. So this, what it does is it allows the warm air between different levels, especially between the 500 millibar level and the 850 millibar level. It allows these air to interact, because this high pressure, so high pressure means warmer air, correct? Air is warm. So warm air is coming. And during winter, in this region, most of the time you have a colder air, because most of Afghanistan and Pakistan here, you have hilly regions which contain cold air because of snow and everything. So when this warm air and cold air interact, it leads to formation of a front, and that front results in formation of clouds and rain. So this western disturbance is nothing but high pressure near Ukraine, which pushes warm air, and that warm air interacts with the colder air, which is the colder air is due to the formation of the subtropical jet stream, and that interaction of the two gives rise to western disturbance, and that's what brings cold weather and winter rain to North India. So when this intrusion of this warm air is missing, then you only have cold weather, because you only have a subtropical jet stream present. Only when this warm air intrusion occurs because of the high pressure which has formed over Ukraine. So whenever I see winter rain for North India, one of the things that I look for is the high pressure ridge over Ukraine. If that has formed, then there is a high chance that there is going to be a winter rain in many parts of North India. So this is the difference between cyclones and extratropical storms, which I think somebody asked me yesterday. What is this extratropical storm? So western disturbance is an extratropical storm, and it is called an extratropical storm because it doesn't have any ocean in it, right? It doesn't form over ocean. It only forms completely over land. So it is mainly due to the mix of warm air and cold air over land. It doesn't move, it doesn't form in the ocean, whereas tropical cyclones form in the ocean. And tropical cyclones moves from east to west, right? All the tropical cyclones moves from east to west, whereas these temperate or extratropical storms like western disturbance, they move from west to east. Okay, and tropical cyclone can affect a comparatively smaller area in the sense that it is very targeted. It can either affect Odisha or Tamil Nadu or Andhra Pradesh or Bangladesh. The effect is much over smaller area, whereas these extratropical storms have a tendency to impact a larger area. So it can produce rain all the way from Afghanistan to Pakistan and all the way to northern part of India, and then finally the Himalayan, because of the presence of Himalayas, these winds they get blocked by the Himalayan ranges and they dissipate out. Okay, so it has a tendency, these extratropical storms have a tendency to impact a larger area, but they don't bring a lot of damages. They only bring rain or snow. They don't bring a lot of damages like a tropical cyclone. Okay, a tropical cyclone doesn't last for more than 7 days. Starting from the lifespan of the cyclone to the end of the cyclone, it is approximately 7 days. Whereas an extratropical storm the duration can be 15 days or even 20 days, because we see these western disturbances giving cold weather or snow or winter rain for a continuous period of time, as long as 15 days or 20 days. So those are the differences between a cyclone and an extratropical storm.
May I ask a few questions regarding western disturbances, please?
Yes, please.
So, firstly, is it possible that remnants of storms over the Atlantic move into the Mediterranean and eventually become western disturbances. Is that correct, or is it like completely wrong?
No, 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 that's not right, because these are so the storms in Atlantic are like cyclones, and whereas this is all over land, and the
Okay.
storms in Atlantic, they move from east to west, right? So they move whatever forms in the Atlantic moves towards US.
Okay.
Whereas this extratropical storm that I'm talking about have a different direction. So there is no
Okay.
chance that it's in something from Atlantic can come here, because something from Atlantic will move in the other direction. So this is
Okay, so but they do sometimes. I mean, from the U.S. coast, they move towards, say, Western Europe.
yes. So those are all extratropical storms. Those are not, yeah. That is the polar vortex. So so okay, let's slightly elaborate. A
Okay.
polar vortex in US, okay, can move all the way towards a polar vortex in the US can move all the way towards Europe. And if there is this ridge present, see, so we have to understand that for the polar vortex to sustain for a very long journey, there has to be some mechanism by which it keeps its energy alive, because all these vortices or the systems that we are talking about, they dissipate out over a period of time. Okay, and in its journey from US to India, it is a 10,000-kilometer long journey. Polar vortex cannot sustain itself for a very long time.
Okay.
Okay. So, but what may happen is the polar vortex can come all the way to Europe, and then near Europe, this ridge, which is the high pressure over Ukraine, could deflect this polar vortex, and then it could actually trigger a storm. But it would be a new storm. It will not be a remnant of that same storm.
Okay.
Okay. So,
And
yeah.
would Western disturbances continue moving towards the Eastern Himalayan region as well?
Yeah. But usually what happens is they don't enter China because or Tibet. The reason is because the Himalayas block these winds, and these winds lose their moisture, because now most of the moisture is kind of dumped on the windward side of Himalayas, which is on the western part of Himalayas. So
Okay.
these don't have a tendency to affect because of the tall Himalayan ranges. If the Himalayan ranges were not that tall, then the impact would be felt on the other side. But these tall Himalayan ranges, they don't allow it to move further.
And what would be the source of, say, winter snowfall for, say, parts of Arunachal Pradesh or Bhutan?
Um, that's the so yeah, so I have not looked into it. Maybe I will look into it and let you know, because I don't have an answer right now. What is the source? I don't know what could be the source, because it probably is. See, so the snowfall is mainly related to two things. One is the jet stream dipping down, and second is
Mhm.
elevation. So elevation plays a very important role, because
Right.
something which is at an altitude of let us say 3,000 meters, it is bound to get snowfall. Like if the winter air, if the cold air dips down to that level. So Arunachal Pradesh, I don't know what is the elevation. So I'm not ready to comment on that yet.
Okay. Thank you.
Yeah, sure. Thanks.
Sir, these western disturbances do not give much rain, no, sir, because those Iran, Iraq, and all are dry region.
No, they don't give. I mean, see, again, we have to understand that the reason it is dry is because this is a ridge. So a ridge exists here. So a ridge is a zone of clear air. Only when it starts coming to India, it dips down. So this is where the trough exists. This is where the trough, and that trough is what allows the formation of a storm. So the initiation of a storm starts from here. That's mainly because the warm air is coming. But the warm air mixing with the cold air happens in this region near Afghanistan, Pakistan, and India.
Okay,
I
sir.
hope it is clear. Along with this, you also have to understand the ridge and trough kind of a pattern, which I told. So this pattern. So these regions will mostly be clear. this trough region is where most of the activity will happen, and we always need to look for these troughing kind of systems. So as this warm air approaches India, it kind of dips down because that's where your jet stream is also dipping down, and that leads to winter rain. So over Iran, Iraq, it is not conducive because there is I mean, these winds are not, these trough patterns are not very conducive over these regions. It's only conducive over in the North Indian region.
And in North Atlantic Ocean, some storms are forming now, sir. Those extratropical storms. Is it due to this phenomenon, sir? Around Greenland and all, it used to give heavy rain in Ireland and snowfall also, sir.
That is polar vortex. Polar vortex. Correct.
Okay, sir.
Okay, so we will. Let me just see how we are doing on time. Okay, so let me finish MJO and then we'll take a break for maybe 10 minutes or so. So MJO is one of the largest tropical variabilities in atmosphere, and it is, I say largest tropical variability because it covers the entire globe, moving from one basin to the other. Okay, and I mean, of course, it was first discovered. This movement was first discovered by two scientists who were a part of National Center for Atmospheric Research, and since it's an atmospheric phenomenon mainly, it was seen as a movement of a wave from one region to the other. And although it is an atmospheric phenomenon, but it actually interacts with the ocean because it picks up the moisture needed from the ocean, much needed moisture. So it is a coupling between ocean and atmosphere. Okay, so it propagates east at approximately 4 to 8 meters per second. Okay, so it's basically a wave train. Okay, and what it does is it's a unidirectional wave. By unidirectional, I mean it is just moving in one direction from west to east, and it brings periods of suppressed or convective activity to the region. And primary role of MJO is in controlling the weather between November to April. And it only plays a secondary role during southwest monsoon, as I already discussed, because during the southwest monsoon, the monsoon circulation is the primary controller of rains. But starting from November to April, which is spanning the northeast monsoon season plus the pre-monsoon season, MJO is the player. It is the sole player that controls the weather between these months. So this is just a schematic explaining the periods of dry. So this is now the Madden-Julian oscillation is active over Indian Ocean, whereas it is dry over the Pacific Ocean. So whenever it is active, it will bring periods of rain. Okay. So what people have done is researchers have actually put this Madden-Julian oscillation in a map, in a phase map, where they say that there are different phases of Madden-Julian oscillation, which is starting from 1 to 8. Okay, and they say phase 1 is when it is active over Africa. Phase 2 is when it is active over the West Indian Ocean. Phase 3 is when it is active over West Indian Ocean. And phase 4 is when it starts moving into the maritime continent, which is South China Sea, and then slowly towards Western Pacific, Central Pacific, and Gulf. So 7 and 8 are the Gulf of Mexico, which is US. Okay. So for India, phases 2, 3, and part of phase 4 is very conducive. So whenever the Madden-Julian oscillation is either in phase 2 or phase 3, we definitely get very good systems, okay, low pressure systems or depressions or cyclones. When it is in phase 4, then also it is kind of favorable, but not as favorable as when it is in 2 and 3. So 2 and 3 are the most active phases for us. Okay. So how do you actually look at this Madden-Julian phase plot? So when you look at the Madden-Julian phase plot, then there are two things which are important. One is the phase, how the Madden-Julian oscillation is moving, and it will always have this motion from west to the east. So this is west and this is east. So it will always move from west to east. Okay, and what it will do is it will you can see there are two circles. One is the inner circle and the other is the outer circle. So that inner circle and outer circle actually tell the amplitude of MJO. Okay, So the amplitude of MJO is very important because the amplitude of MJO actually tells whether the moisture convergence or whether the coupling between ocean and atmosphere is strong or weak. A stronger coupling between ocean and atmosphere will give rise to a very strong system, whereas a weaker coupling will not give rise to a very strong system. November 22nd, 23rd, very strong coupling was seen that led to formation of cyclone Nivar. Correct? And later on, it became into a weaker phase. That's when we had cyclone Burevi, which was only a cyclonic storm. It was only a cyclonic storm, whereas Nivar was a very severe cyclonic storm. Okay. So the amplitude of MJO is also important along with the phases. Okay, so we are always on the lookout for whether the amplitude is strong or weak, because strong amplitude will always lead to a formation of a strong system. So this is the Madden oscillation plot from IIT Pune. I will show you where to find this in the afternoon period. You can also look at Madden oscillation plots from other models, which is ECMWF model also has a plot. But more or less all the plots will look very similar. Okay, more or less all the plots will look very similar. So if you are really interested in actually learning about Madden oscillation and how to predict Madden oscillation, then there is a very nice research paper which is available, which was done by Wheeler and Hendon. This was a cutting edge paper on Madden oscillation because it actually tells you how to get this phase plot. Okay, what goes on to get this particular phase plot, because this phase plot tells me a lot of interesting information, especially during November and April, because November and April is the season when you have cyclones in the Bay of Bengal and Arabian Sea, and March, April, May is also the season when you have cyclones in both the basins. So it tells me a lot of information. So let me not get into the gory details, but let me just tell you one thing. The Madden-Julian oscillation forecast depends on three things. One is the 850 HPA wind, zonal wind, the 200 HPA zonal wind, and the outgoing long wave radiation. Using these three data sets, I make this MJO plot. Okay, I make this MJO plot. And that's pretty much what I will try to say, because if you want, I can get into the details. But in order to get this MJO plot, you do a very complex. There is an algorithm which is known as an empirical orthogonal function. It is a mathematical algorithm, mathematics-based algorithm, which actually takes all these three data and tries to find a correlation between these three data. And when the correlation is very high over Indian Ocean, it says that the Madden oscillation is going to be in the Indian Ocean. When the correlation is very high in the Atlantic, it says that MJO is going to be in the Atlantic, and it puts points, and that's how you get the phase plot. Amplitude is basically the correlation. Again, the high correlation between this means high amplitude. Lower correlation means low amplitude. So that amplitude value is also anything outside of this inner circle means very high amplitude. Okay, so let's not get into too much of technicalities, but let me just say that in order to predict Madden oscillation, scientists actually look for the 850 HPA, the 200 HPA, and the satellite-based outgoing long wave radiation data. So again and again, the 850 HPA data becomes very, very important. In data becomes very important because it also helps us in finding the Madden-Julian oscillation feature. Okay, so we'll take a 10-minute break and we'll come back at around 11:40. If there are any doubts, I will be happy to answer right now.
Okay. Professor,
yes.
They are saying that that instead of looking at phase plot for MJO prediction and I mean for following MJO progress, movement and prediction, it is better to use plots like of the type that Hovmöller type of plots that shows that we can get from NCICS.
But the thing is, yeah, the Hovmöller plot also uses the same technique to tell the MJO movement.
Yeah. Then why do they say that? I think maybe because it doesn't it doesn't show the distribution of. I do not know what's probably missing, but generally these amateur weather bloggers, they say, "Oh, this is." I mean, the good ones among the amateur weather bloggers say that let's not look at phase plot. Let's look at NCICS. This for this. Why is that?
I'm not too sure because both of them. So I maybe they don't know the difference between the probably, but whatever is the so see so finding out the Madden-Julian oscillation is the key, and there is only at least one proven technique which is present.
Okay, this one.
That particular technique, either you can put it on a phase plot or you can put it on a Hovmöller type of diagram. It is the same thing because both of them are same because Hovmöller diagram is also telling me whether the MJO is in the Indian Ocean or in the maritime continent, and this phase plot is also telling me the same thing. Because if I look at if I loop around, so let us say this is what I showed you. So it is telling me when is the MJO in the Indian Ocean during which time, and Hovmöller diagram also tells me the same thing because it is longitude versus time. So I don't know what extra information that is giving, which I don't know why they are saying that. I'm not too sure.
Okay, I will find out. Thanks.
Right. So yeah, but
Sir,
the phase plot makes a lot of sense because this has been formed after looking at a lot of math. I mean, so this complex orthogonal function is a very what do you call it? It's a very strong tool to find out correlations between different data sets, especially the wind and outgoing radiation, because the wind and outgoing radiation is mainly the cloudiness. So if the cloudiness is reduced and the wind is conducive, then that means that it will couple together and lead to a stronger air-sea coupling, resulting in a much better formation of a system. So physically speaking, whatever we want is present here. And Hovmöller diagram is just a diagram which tells you, which just takes this MGO data and plots it on a different kind of a pattern. I'll just show you that. So it just plots this on a different diagram. Like this is again, so phase plot is giving me the same thing, which is 0 to 0 is this is Indian Ocean, this is maritime continent. So and these are the days. So it tells me the same thing. Like between 9th May and 23rd May, there was a MGO in the Indian Ocean, and the phase plot is also telling me the same thing.
Perhaps the cloudiness distribution. I mean, geographically, the distribution of clouds may give some info. I do not know what these guys are saying. I will find out.
Yeah, if you can find out and let me know, that would be.
Would you take these the resolution in the Hovmöller plots too seriously? I'm not sure if we should take those resolutions too seriously because these are not really high resolution. These are I wouldn't, for example, okay, 80 East, Chennai is in 80 East. Let me draw a line, vertical line at this and see where the cloudiness. That's probably not the method to go, I guess.
No, that's not right. Because see, again, these are just guidance. These are not to be taken with what you are saying. You cannot draw a line and say that there is a lot of cloudiness over Tamil Nadu. No, you cannot do that, right?
Okay.
This is just a guidance that there is a coupling between the waves and the MJO. So there is a high probability that a strong system may form. So it is again giving you a overall picture of what is going to happen in the Indian Ocean or in one of these basins. Right.
Okay, cool. Thank you.
Hello.
Yeah.
Yeah, sir. I have a very basic doubt regarding subtropical storms. So, could you just go to the slide where you mentioned the difference between subtropical and extratropical storms? Yeah. So I remember reading something about subtropical storms or cyclones moving from east to west. So, is this the case with every single tropical cyclone?
Tropical cyclone east to west. Yeah, tropical cyclones move from east to west.
So is you talking about the direction of like in which the cyclone moves?
Yeah, right.
Okay, but like there have been cases like say cyclone Nisarga, which formed in the Arabian Sea and then moved eastwards and made landfall towards on the Mumbai coast. So that moved from west to east, correct?
Okay, so when I think so generally the thing is when the tropical cyclones move, they move from east to west, and as they are moving from east to west, they have a tendency to make a northward track as well, and that is due to the presence of ridges, which I will talk when we talk about cyclones.
Okay.
So east to west is that if you track any cyclone, then it always starts as a east to west movement, and then it may track up north as well. So that is possible. But I'm just giving a general scenario. That's all.
Okay.
Like general scenario between a tropical cyclone and an extratropical cyclone is tropical cyclones will always start moving from east to west, whereas temperate cyclones will always start moving from west to east.
Okay. Got it.
Sir, in Twitter, I saw that some are telling that those western disturbance will pull the systems towards north. Sir, can you please explain that, sir?
Which system towards the north?
Yes, sir. They are telling that western disturbance, if the western disturbance is active, it will pull the system towards north, sir. In the Bay of Bengal, can you please tell about that, sir?
Which so a low pressure system?
Yes, sir. Low pressure system.
I don't know. I'm not too sure about that. Yeah. So by in Twitter, is it some? I mean, so if it is a scientist who have put this up, then maybe
Not
it's.
scientists, sir. Enthusiasts are telling about.
No, no. I mean, I would not. I like to comment on that because I'm not too sure what to see. So there are a lot of misinformation that is present on many social platforms. So
Okay,
yeah, I'm not sure what exactly is the scenario. So unless the complete scenario is given to me, I don't want to comment on that. So you're just making a blanket statement, but I would like to know the complete scenario. Like where is the system, which
okay, sir.
longitude, what is the MJO presence, what is the waves presence. So if it is a complete package, then I can explain. Just
During
by
Nivar, I think they are telling like that.
I think they
During the
are
Nivar
discussing
cyclone.
the trough associated with the western disturbance and that the low pressure system in Bay of Bengal, they may interact and there might be a transfer of energy, especially when the trough associated with the western disturbance has the is the stronger of the two. This is not something that always happens, but it could happen. As you could see, there are two low pressure systems. Not both are not low pressure systems. The trough associated with the western disturbance could, you know, uh, pull this low pressure in the Bay of Bengal to the north because of the energy transfer that could happen. I mean, we have seen this many times with the northeast recurving cyclones. I think this is just based on observation, not a scientific.
That is clear. That is, I don't think it will pull it up. That is the reason is because once the western disturbance forms, once if the cyclone interacts with the western disturbance, then the steering will be now done by western disturbance. So this was a very clear case with the cyclone Maha, which formed last year in Arabian Sea, which gave rains to Mumbai even in November, and it got stuck in this westerly trough, and it did so. That is more like a steering. I don't think cyclones can be affected by western disturbance because cyclones are a much stronger system, whereas western disturbance are a weaker system because they form mostly on the land. So the pull up of this thing, I don't kind of buy it, but I can completely understand why it would get pulled, because now let's say this is the western disturbance and the cyclone is moving like this, so it can get caught in this westerly trough, and then it can move along with the western disturbance. So so western disturbance will steer the cyclone. So steering is the right word there.
That is what is meant by that. That's what. So the direction of the cyclone or the track of the cyclone is altered by the incoming westerly jet, the westerly trough.
That is absolutely possible because cyclones are very strong structure, and the steering of cyclone is usually done by 500 millibar level wind levels. 500 millibar level wind is what steers the cyclone.
Okay, sir.
So steering wind for a cyclone is 500 millibar, whereas steering wind for other systems like low pressure is 700 millibar. So if you are interested in looking at the steering of cyclones, then you have to look at the 500 millibar chart. And most of the time, if the westerly trough is not present, then the cyclone will actually move from east to west.
But if there is a should move to in the northwest direction because of the Coriolis effect, right?
It will move to the north direction because of the ridge. So I have a slide on. We have a separate session on cyclone. Just during that time, I'll explain the northward movement as well.
Yeah. Okay.
Sir, can we students predict the MJO model, sir? Can we draw our own model on this, sir? Or does it need specialization, sir?
No, if you want to track your own MJO, then you have to read this paper completely, and you have to write your own code, which is this empirical orthogonal function, which actually takes this data. Then you can actually produce these kind of charts.
Anush, I think we can do it because
okay,
the
sir.
paper is probably going to give you the algorithm, and we just need to find a way to implement that. I don't know, in MATLAB, Python, C, or whatever.
I don't have the algorithm.
I mean, I'm not expecting this to be an easy job, but we could.
This is not at all. Yeah, it's not an easy job, but see, the point is that whatever you are going to get will be the same as what is present in these other ECMWF or IITM. The reason I am saying is that because you are going to use the same data, because they also use the same forecasted data from CFS. So all of these actually use the forecasted data from CFS, which is the 7-day U wind, and the OLR data from GFS. So if you are going to use the same data, then I'm not sure what extra you are going to get. Additionally, you're going, unless you change the way you are looking at MJO, unless you introduce your own knowledge that something which is missing. Okay, but if you are going to use the same data and if you're going to use the same methodology that is being given by Wheeler and Hendon, then I'm not sure what extra thing you are going to produce. So I don't see the point in reproducing the chart. Maybe if you are interested, you can